substitution, nucleophilic, bimolecular, or the SN2 reaction. So substitution reactions can occur with things like alkyl halides because they contain something that is readily replaced. So something like a halogen, which once it's displaced from the molecule is a weak base. So groups that are very weak bases, like halogens, chloride, bromide, and iodide, are good leaving groups. And so they can be replaced, as in this case, this chloride is being replaced with a hydroxide ion to give an alcohol as a product. So the bimolecular has to do with the reaction mechanism, which then ties into the rate of the reaction. This is a concerted reaction. So in the mechanism, so here is our starting alkyl halide, right? The carbon that alkyl halide is bound to has a partially positive charge, and that's because your halogen will have a partial negative charge. And so that makes this carbon atom electrophilic and able to react with a nucleophile. And so the nucleophile in this reaction is the hydroxide ion. So we need to remember when we see something like sodium or potassium attached to a complex ion, that means that the sodium or potassium is always going to have a positive charge. So whatever it's attached to has a negative charge. And that would be a base or a nucleophile in a reaction. And so this is acting as a nucleophile because we are replacing the chloride. And so the mechanism of this reaction takes place all in one step. So we have a hydroxide ion with its negative charge that will be attracted to that positively charged carbon. So we form a new bond to that carbon and break the bond to the chloride. And so this is the only step of this mechanism. There's two molecules involved. That's where the bimolecular comes from. And so the rate of this reaction is equal to a rate constant times the concentration of the two things involved, the alkyl halide and the nucleophile. Okay, and so only one step. What I'm going to draw next is the transition state for this reaction. And so we have a carbon atom there in the center, right? And whenever we draw a transition state, we're going to draw bonds that are partially formed or partially broken as dash bonds. And so one thing that's hard to represent on a two-dimensional piece of paper is the fact that this nucleophile is attacking from opposite the leaving group. It's basically coming up from behind and pushing it out of the way. And I can indicate this in the transition state by putting them 180 degrees apart. So I can say I've got a partial bond forming to that hydroxide. I'm partially breaking the bond to that chlorine. And then I want to represent everything else that's attached to that carbon. It's got the rest of the carbon chain, which is 1, 2, 3. So CH2, CH2, CH3. And it also has two hydrogens, right? Because in our initial structure, we could only see two bonds, right? We know carbon's neutral when it has 4 bonds. The remaining 2 bonds must be bonds to hydrogen. And so that is the transition state for this reaction. Okay. Notice that there are 5 things bound to that carbon atom or partially bound. Carbon is a pretty small element, and typically it does not violate the octet rule. It's going to have only 4 bonds. And so if you're going to squeeze 5 things around that carbon, even temporarily in a transition state, the groups on that carbon atom should be small. So an ideal substrate for this reaction would have as many hydrogens, we can't get any smaller than that, as possible attached to that carbon. So the best substrates for SN2 reactions would be when all 3 of those groups are hydrogens. So that would be a methyl halide. So that would react the fastest in an SN2 reaction. The next best thing would be something like this, which is a primary alkyl halide. And then secondary alkyl halides can, with the right nucleophile, also undergo an SN2 reaction. And tertiary alkyl halides cannot. Tertiary alkyl halides are too crowded If you treat them with a base, you're going to get an E2 elimination instead. Okay. So this is essentially the order of reactivity, right? So the methyl halide would react the fastest, and the secondary would be the slowest in this scheme. And then we'll say the tertiary alkyl halides, that this is not going to happen at all. So we'll cross that off. Okay. So let's complete this mechanism and get to the product. So we've added that alcohol. Okay. And so what we can see in this transition state is that the bond to the alcohol is opposite where the bond to the halogen was. And so that doesn't make any difference in this example reaction. But if this reaction were to occur on a secondary alkyl halide that had a chiral center, you'd essentially be having your highest priority group opposite where the other highest priority group was, right? Because what you're kicking off from here, the chloride, would have been the highest priority group, and what you're replacing it with is now the highest priority group, and it's on the opposite side. So what this means in terms of stereochemistry is that if the reaction occurs at a chiral center, so if your reaction is at a chiral center, the chirality inverts. And that's because your highest priority group would be on the opposite side of where it used to be. So you're essentially switching two groups, and we know that that will switch a chiral center. Okay. And so we've looked at the mechanism, we've looked at the rate, the substrate. The ideal nucleophile for an SN2 reaction is going to be a strong nucleophile, or say a good nucleophile. Right, so if we're wanting to take a primary alkyl halide and make an alcohol, the two possibilities for a nucleophile would be neutral water or the negatively charged hydroxide ion. The negatively charged hydroxide ion would be the better nucleophile. So you'd pick that rather than water. One thing to watch out for is a lot of our nucleophiles that are good nucleophiles can also be strong bases. So you need to keep an eye on competing E2 reactions. And that might depend on the structure of a substrate. The more substituted it is with a secondary alkyl halide, you'd have more danger of that competing E2. Another factor with that would be the temperature. Higher temperatures tend to promote elimination reactions. So if you have a higher temperature and these sort of conditions, one of these substrates and a really good nucleophile or base, that might be pushing the reaction towards an E2 pathway instead. Okay, and finally, the last thing I want to mention is the solvent. And I put solvent last because it's not something that determines the reaction pathway. It's rather something that can support the rate of the reaction. And so for an SN2 reaction, you want a good nucleophile. So you want a solvent that's not going to interfere with your nucleophile, right? So a solvent that was protic, that had a partial positive charge on hydrogen, would surround a nucleophile and kind of slow it down. So for an SN2 reaction, it would be faster in a polar solvent. Right? We still got charged species, we still need it to be polar, but we'd prefer it to be aprotic.